Hello everybody, and welcome back to another Big Ideas Geometry lesson. Today we're going to take a look at section 8.4, Proportionality Theorems. Now, before we talk proportionality theorems, we need to talk about what a proportion is. In the past couple of lessons, we referred to a statement of proportionality, and we've been sort of throwing that word around a lot, or that phrase around a lot. A statement of proportionality is a statement that two fractions, or ratios, are equal. Now, there are a couple of ways of making a proportion, but the most obvious example is we've already sort of been doing them. Let's take a look at the following two triangles. Let's actually write them up here for right now. Let's say we've got a small triangle like this. We'll call it A, B, C. And let's make a larger triangle. We're going to call it D, E, F. And if these two triangles are similar to each other, we know, no matter what, that we can divide one of the sides of our second triangle by one of the sides of our first triangle. We could do DE over AB, for instance. Let's pretend for a second that AB is 1, ED is 3. If we think about it in numbers, this is 3 divided by 1. Now, we could also make a statement of proportionality using a second side. Let's say EF and BC. What this is saying is, no matter what fractions we get, if these two triangles are similar, this fraction will be the same as this fraction. So let's say EF was 9 units long and BC was 3. Well, we could say 3 over 1 from before equals 9 over 3, which it does. They both make 3. That's what we're talking about when we say proportionality. We're talking about this statement here. So the triangle proportionality theorem deals very specifically with what happens when you have parts of a triangle compared to other parts of a triangle. I'd like you to draw out this triangle here. It's going to be a sideways isosceles triangle. And I'd like you to draw a line cutting through it, like so. I'm going to label this triangle A, B, C, D, E, like that. Now we end up with two triangles. A small triangle, BCD, and a larger triangle, ACE. So we can actually compare these two triangles. We know that in similar triangles, we can compare similar sides. So we could say that BC, the top side of the smaller triangle, has to equal AC, this entire length, because that's the top side of the bigger triangle. But this brings up something interesting. If these are sharing the same part of a triangle, wouldn't that also mean that BC is proportional to AB? Let's say BC is 6 and AB is 2. We could compare these two. We could make a proportion that says BC over AB is 6 divided by 2. Now let's say at the bottom side is 9 and 3. We might start to see what's going on here. 6 over 2 is 3. 9 over 3 is 3. These two sides are proportional. Even though we're just dealing with a piece of a side, with AB and ED, they're still going to be proportional. So the triangle proportionality theorem says this. It says that we can specifically compare any parts of these two triangles under one big condition. AE and BD have to be parallel because that's enough to make the triangle similar. So the theorem itself says this. If a line parallel to one side of a triangle intersects the other two sides, then it divides the two sides proportionally. There we go. What this means is we could set up a proportion, 6 over 2 equals 9 over 3. In fact, I'm going to color code it. I'm going to say 6 over 2 in red equals 9 over 3 in blue. But a proportion is just something that compares two lengths on two triangles. It doesn't say that we have to compare small triangle to big triangle. In a proportion, we are allowed to compare any two corresponding parts. So we could also say that 6 over 9, the top length of the small triangle divided by the bottom length of the small triangle, could also be compared to 2 over 3. The top smaller length divided by the bottom smaller length. I mean, it still works because we're comparing top to bottom, top to bottom. I see no difference in comparing 6 divided by 9 to 2 over 3, as opposed to comparing 6 divided by 2 on this top side divided by 9 over 3. It's the same deal. In fact, you will see that while we get different numbers, like 6 over 2 and 9 over 3 are 3, whereas these are 2/3, it's still consistent, they're still proportional. This also gives way to the triangle proportionality converse. Remember that a converse is just the opposite of a statement. So the converse would say, if a line divides two sides of a triangle proportionally, meaning if the proportions are consistent and stay the same the whole way through, then it is parallel to the third side. Nice. Let's take a look at examples 1 and 2. So example 1, we are comparing the different lengths of this set of two triangles here. It really is one triangle that is split up a little bit. That said, we can actually go through and do this. We are told that RS is 4, ST is 6. We are told that QU is 9. We are not told what RQ is, and we really need to find that length. Let's call this one length X. We can solve this using proportions. So, because these lines are parallel, we can set up a variety of different proportions. One thing we could compare is we could compare the top triangle to the bottom triangle, red side to blue side. So, if we're comparing top to bottom, that'd be 4 divided by 6, and that's supposed to equal top to bottom, x divided by 9. That's one way we could set this up. But there are other ways we could set it up too. We could also compare, instead of just right side and then equals the left side, we could compare the two lengths of the top triangle to the two lengths of the bottom. We could say something more like 4 divided by x equals 6 divided by 9. And guess what? We're still going to get the same answer. So let's talk about solving proportions, since it's been a minute for some of us. Anytime you have a proportion, we can cross multiply to solve. So 6 times x is 6x, 4 times 9 is 36, and then we know that we can just divide by 6, willy-nilly, x equals 6. Even if we did the cross multiplication on this one, we'll see that it works out the same way. X times 6 is 6x, 4 times 9 is 36. It's the same equation. So when we simplify it, we get the same answer. No matter how you set up your proportion, as long as you're consistent and you mention the corresponding parts, you can do it. Very nice. I'd like you to see if you can use this idea to determine if PS and QR are parallel. Remember, these lines are only parallel if we can test the sides and prove that they're proportional. So, pause the video here and see if we can do it. How did we do? In this problem, we can compare any corresponding parts to each other. So we can compare 90 and 50, for instance, to 72 and 40 to see if they're proportional. Well, 90 divided by 50 should equal 72 over 40 in this case. And there are two ways of solving this. One is you can just simplify both of these fractions. You get 9/5 equals 9/5, which is true. But another way is we can cross multiply just like before. 50 times 72 is 3,600. 90 times 40 is 3,600. Yeah, it's proportional. That means that PS must be parallel to QR. Nice. Before we flip the page, let's talk about the last two theorems. The three lines parallel theorem looks something like this. Let's draw out a big triangle here, where we have, you guessed it, three lines that cut through it, all of which are parallel. And let's call this triangle A, B, C, D, E, F, G. A lot of letters. In fact, it kind of looks like a carrot, so I'm going to draw it as a carrot. Why not? The idea is, if we have three lines that are all parallel to each other, that means that all parts of these triangles should be proportional. We can say that AB and GF correspond. So AB over GF should equal, well, BC and FE correspond. So BC over FE, which corresponds to CD over ED, which corresponds to the entire bottom length AD and the entire top length GD. And we could go on and on and on comparing these parts. No matter what, every piece of these triangles is proportional. It's going to be the same proportion. So the three lines parallel theorem says this. It says, if three parallel lines intersect two transversals, then they divide the transversals proportionally. If three parallel lines intersect two transversals, they divide the transversals proportionally. Last, but most certainly not least, with the triangle angle bisector theorem. Let's draw a triangle that looks something like this. Let's call it, well, let's not name it yet. Let's put a line through it, specifically a ray, that juts through it like this. Now, I'm going to call this triangle A, B, C, this point here will be D, but I want to make something very clear. CD is not congruent to DA. It doesn't need to be. All that needs to be congruent are these two angles formed by the ray. The ray here is bisecting an angle, angle B. It's cutting it in half. And the rule is this. If you have a ray bisecting an angle, then the pieces of the triangle that are on the other side, like CD and DA, are proportional to the full lengths that still remain, like CB and AB. If CD is 3 and CB is 5, what this means is this side is proportional to this side. 3 could be proportional to, I don't know, 6. Let's say that these are times 2. This would be 5 times 2, which is 10. We have proportionality happening here. So, what we're going to do is we're going to write down the definition for this theorem. And I want to warn you that it's a bit of a longer one, so be prepared. The triangle angle bisector theorem says this. If a ray bisects an angle of a triangle, then it divides the opposite side into segments. We know that these segments are CD and DA, segments whose lengths are proportional to the lengths of the other sides. These pieces of a line segment, CA, are proportional to these full sides, CB and AB. So let's flip the page, take a look at example 3. In this diagram, for example 3, we know that angles 1, 2, and 3 are congruent. Cool. We are also given some lengths of streets here. GF is 120, DE is 150, and CD is 300. We're trying to find the distance HF, which is this entire segment here. This entire segment is our unknown, which I'm going to call X. So the question is, what can we compare X to set up a proportion? Well, X is the entire left side here from F to H. If we wanted to find the corresponding part to this, this would be the entire right side. The entire right side being E to C. But there's one problem. This only works if the lines are parallel. So we're stuck. Except we know that angles 1, 2, and 3 are congruent. We also know that these angles are corresponding. They're in the same spots. So because of the corresponding angles converse, if corresponding angles are congruent, the lines are parallel. 1's congruent to 2, so they're parallel. 2's congruent to 3, so they're parallel. 1's congruent to 3, so they're parallel. They're all parallel. So we can actually go through and set up a proportion. Now again, this proportion is comparing the entire left side to the entire right side. The entire right side is 150 plus 300. 150 plus 300 is 450. Okay, we got one part of our proportion, but what can we compare it to? We need to compare it to a length we know on the left side, because that's what we started with, and a length we know on the right side. That's what we ended with. The only length we know on the left side is 120 yards, but what can we compare that to? On the opposite side, we have 150. So this is our proportion. When we go through and solve this proportion, we will end up multiplying 150 times x, and that's going to equal 650 times 120. When we solve all of this and get all the way to the end, we should get x equals 360 yards. There we go. Was there another way to solve this? Absolutely. We could have instead solved for this missing space, GH. We could set up a proportion like GH over 300 equals 120 over 150, and then just added our result to 120 again to get the entire side. But it's easier if we set up just one proportion, right? All right. With these next three examples, we are going to be using the triangle angle bisector theorem to solve them. I'm going to start with part B here. Part A is a very challenging problem. I'd be happy to go over it at the end. Part C is a little tough, but we can manage it. But part B is the most similar to what we've been dealing with. So let's take a look. In part B, we have a ray that is bisecting angle V, which means that the corresponding parts are as follows. This small section is corresponding to this section. This small section corresponds to this one. So we can set up a proportion or two. You get to choose whether you want to do 14 over 24 equals x over 48, or you could do it like I like to do it, which is to compare 14 to x, the small chunk of the divided side divided by the big chunk of the divided side, equaling 24 over 48, the small whole side divided by the big whole side. When we cross multiply and solve this, you're going to get x equals 28. Now I want you to pause and try out problem C, then try out problem A. I'm going to unpause in just a moment, so pause the video and see how you do. How'd you do? In part C, the answer is going to be 4 root 2, or if you did it in terms of decimals, you could have gotten 5.65 as well. For part A, I want to talk a little bit more in depth about, because we have a problem. QR isn't given, and in order to set up proportions, we need QR. So, in order to set up this proportion, we need to figure out a way to represent QR. Well, the entire line is 15. This part of the line is x, so QR could be written as 15 minus x. We could say that 15 minus x divided by x equals 7 over 13. When we start multiplying this one out, we're going to get 13 times 15 minus x equals 7x, which is 195 minus 13x equals 7x. When we add the 13x to both sides, we get 195 equals, 20x. And when we divide by 20, we get 9.75. Cool. Last problem of the unit, folks. Example 5. Now, this example is actually hitting pretty close to home because Lakeshore Drive is an actual street near me. The real estate term lake frontage just means the distance along the edge of a piece of property that touches a lake. The reason why lake frontage is so important is because a lot of homes are valued higher if they have a lot of lake frontage. So it deals with the property value. We're asked to find the lake frontage to the nearest tenth of each lot shown. In other words, we have to find, if I zoom a little bit, how much lake frontage there is in lot A, how much lake frontage there is in lot B, and how much lake frontage there is in lot C. The problem is, if we look at each individual lot, there's not a ton we can compare. Like, we know that we can compare A to 48 because the lake frontage and the frontage of the house should be comparable. They're corresponding parts. But then we get stuck. There's nothing else to compare in lot A. So what? Are we just doomed? Not quite. Recall that on the front page, when we had this diagram, I also mentioned that the entire length could be compared to the entire length. With these lake frontages, we can find the total length of the lake and the total length of the street. So let's do this. The total length of the street, Lakeshore Drive, is 48 plus 55 plus 61. That's going to be 164 yards for the entire street. So now we can actually finish our proportion. Because we're comparing the lake frontage to the lot frontage, we can compare the length's distance to all these lots' total distance. And we can do the same for B and C as well. B over 55, it's also going to be comparable to the full lake divided by the full street. Same with C. C over 61, lake frontage over lot frontage, equals 174 divided by 164. Very nice. So, when we actually do the calculations for these, I believe we get 50.9 for the first lot over there. I believe for the second lot here, we're going to get 58.4. And for the third lot over here, I believe we are going to get 64.7. That's part A. Part B says, in general, the more lake frontage a lot has, the higher its selling price. So which of these lots is the most expensive? Well, we know that the lakefront property with the most frontage, or lake frontage, should have the highest price value, so that'll be Lot C. I'm putting $3 signs there. Lot B is the second highest, so I'll put some dollar signs here. And Lot A will be the cheapest. Part C deals with the prices of the lake frontages. And it tells the least expensive lot, which is Lot A, should be $250,000. We're trying to find the prices of the other lots. The good news is this. If you know the lake frontage and you can compare it to the price, couldn't you compare the lake frontage to the price of these other two as well? So we could set up a proportion. $250,000 divided by 50.9 yards of lake frontage could be compared to 58.4 yards of lake frontage for an unknown price. When we solve this, we'll get the price of B. In fact, if we put this in our calculators and solve it, we should get that the price of B is going to be a little bit higher than the price of A. We should get the price of B is $286,000, $286,000, 836 and 94 cents. Last, most certainly not least, we can do the same thing with C. So we can compare 250,000 over 50.9 and say that that equals x over 64.7. Once again, we plug all this into our calculators, and when we do, we should get $317,779.96. There we go. This concludes our lesson for today, everybody. Thank you so much for listening, and have a fantastic rest of your day.